I think
Yeah, absolutely. Absolutely. Sure.
Should we get started, Joycee? Maybe in the interest of time.
Yes, yes, sure.
So, good morning, everybody. Uh, Welcome back to day 4. And today we have an interesting set of talks on advanced processor and memory technologies. Very happy to welcome Joycee Meckie from Iit Gandhinagar. She's a faculty member at Iit Gandhinagar. Her research interests are in approximate computing, asynchronous design, low power memory systems, etc. Over to you, Joycee. Please feel free to tell us a little bit more about your interests and get started with the the talk on asynchronous processes. We are all eager to hear from you.
Yeah, thank you so much, Professor Madhura. I'll just share my screen. Okay. Okay, so I'm not able to share my video somehow. Okay, so, okay. Is my presentation visible to everyone?
Yes, ma'am.
Right. Fine.
Okay, thank you so much. Okay, a warm welcome to all of you for today's morning session. And I'm very happy to be here today to give a short presentation on asynchronous processors. So before I get started, let me just give a very quick introduction about IIT Gandhinagar for some of you, and also what we are doing in our group here. So IIT Gandhinagar is situated in Gujarat, and it started as people call it as a second generation IITs. We started in August 2008, and I have been associated with IIT Gandhinagar for more than 10 years now, and it has been a very nice journey all these years. I work in electrical engineering, mainly VLSI design. So my interests are, as Professor Madhura mentioned, approximate computing. So that's one of the topics where we are exploring how approximate computing can be useful to design hardware which can tolerate hardware for applications which can tolerate errors. For example, machine learning algorithms or image processing algorithms or video processing, where let's say that if there are some errors in the process in the implementation, you would not see the effect finally in the application, or you can ignore the effect, let's put it that way. So that is one of the areas in which I'm working. The main motivation to explore approximate computing is to see how we can reduce energy for computing. So that is the main motivation. We have looked at approximate arithmetic circuits and also approximate memories in this context. There is an interesting research area where we can design ultra low power memory if we can allow more errors. So we have figured out that, or I think people know already, that there is a lot of effort that goes into designing memories that don't have errors. And if we can somehow allow errors, and still if the application does not fail or does not or can, the errors can be ignored, you can benefit by using approximate memories. So that is the whole area of approximate computing. The second area in which I work is called radiation hardened systems. So we design circuits for space applications. This project actually started with a couple of discussions that we had with ISRO, Space Application Center, which is situated in Ahmedabad. And we were trying to explore how we can build radiation hardened systems. And one of the projects that emerged out of this discussion was, can we think of asynchronous processor, which is radiation hardened. So that was a very interesting sort of, work that just emerged out of two completely unrelated projects. Since I was already working in asynchronous design, just as more like an extension of my own doctoral thesis. And then as I ventured into radiation hardened systems, we figured out, okay, we may want to try something related to asynchronous and radiation hardened systems. That's how that project emerged. If there is a little bit of time, I'll probably present some results that we have from that work, because it is related to asynchronous processors. And then, of course, as I said, we have recently tried implementing asynchronous processor. As we go along in this talk, I'll talk a little bit more about that topic. We work in near memory and in-memory computing architectures also. This is an emerging area. In-memory computing basically means that you can compute within the memory without transferring the data into the processor. This is an interesting topic because many of the emerging workloads, like ML workloads, for example, have a lot of computing involved. And it makes sense to do the compute where data resides, which is basically the memory. So currently we are looking at caches. Yeah, actually, I'm not able to see the chat box. So if anyone has a question or doubt or anything, please feel free to unmute and ask. That will be easier. So in this in-memory computing, what we have explored is design of SRAMs largely. Many people are also working in DRAMs, but we have largely explored SRAMs, and our goal is to eventually come up with an IP core which will be completely an independent IP core which can support in-memory computing and can be merged with any other SOC in general. That is the goal of that project. And Lastly, we are also doing a lot of timing analysis kind of work in the lab, exploring new tools which can help in doing a better timing analysis of the circuits. So, and we also work on FPGAs to some extent, trying to implement machine learning workloads on FPGAs using their HLS tools. So that is a brief overview of what we are doing here. And as we go along, we'll discuss more of what kind of projects are possible. Okay, so I'm told that this has to be a very interactive session, so I'll also try to keep it very interactive as we go along. Okay, so can anyone tell, or is there anyone who has heard about asynchronous systems or logic or circuits before this presentation in any context?
Will fast interrupts count?
Okay, and yeah, okay. Any other? And so asynchronous circuit style or logic style?
They don't have a common clock.
Yeah, they don't have a common clock. Okay. What else? Okay, I want to ask another question. So, is there a potential for exploring asynchronous design at all, or do you see any reason with the emerging, SOCs and chips? Is there any reason one should explore asynchronous design?
Yes, to mitigate the need of clock tree.
Yeah, okay. So let me just give you a little bit of an overview here. So the most or the easiest place, where we can think of asynchronicity coming into chips is when we talk about multiple clock domains, right? Multi-clock domains as it is called. So many SOCs are today that we see are multi-clock domains, right? And so each clock domain is internally having its own clock distribution tree, and this distribution tree is local to that particular IP on the SOC. And when many such IPs are connected, then by nature they become asynchronous with respect to each other because the overall global timing may be lost. So either the designer makes a significant effort to ensure that the global timing is known to every IP, or you just assume that everything is asynchronous, and then all the related hardware has to be in place so that the communication happens error free, right? So this is the easiest example I can give for asynchronous processors. Now this design style emerged around 20 years back or so, when people started to have some interest in asynchronous design. Today people are using asynchronous design, or are trying to use rather asynchronous design for what we called as neuromorphic architectures, because it is related to how chips are designed based on human brain, the working of human brain. And we know that that it is purely asynchronous, right? The way neurons spike. So that's the emerging areas in which asynchronous has found some place. Okay, so it's definitely not the mainstream for logic design. And so we will, in this talk, what I want to do is I want to show some of the some of the intricacies of how one would design asynchronous logic, and that should help you to understand why it is not the mainstream processors. And also I want to motivate that which all applications would benefit by having asynchronous design. Okay, so that will be these are the two goals hopefully I should be able to meet. So very quickly, we all know how synchronous circuits are designed. This can be a typical pipeline architecture. And we know that in a synchronous design, the combinational logic is separately designed, and then they are connected through interstage buffers. And we figure out the maximum clock period, which is the maximum clock frequency at which it can operate by doing what is called as timing analysis, right? So now when we don't have a synchronous circuit, and when we want to convert this into an asynchronous circuit, what would happen? What changes will we see? So this is one way in which an asynchronous circuit can be connected. So these slides are from one of the tutorials that was taken long time back, and it will make some sense because these are very basic or fundamentals of asynchronous circuit. So as you can see here, what is going on is, maybe I can use, yeah. So what is going on is, you can see that there is a request that comes in, and this request sort of forwards the data from here to here, and it enters into this combinational block. And then this combinational block generates a signal which says that, okay, I am done. And that done signal, turns on this set of registers or the interstage buffers. And then this data is passed on to the next stage. And then again, this computes and it generates a done signal. And that's how the data is forwarded. So it is the job of the combinational circuit to generate what are called as done signals, so that the data can progress. Now this paradigm, this paradigm, as you can see, works for circuits where this CL is completely independent of this CL, or for example, if this CL is a very large stage as compared to this CL, then this kind of a circuit benefits, because in a synchronous design, in the previous slide that we saw, the clock period is fixed, right, between the interstage buffers. So the maximum clock delay, let's say if the maximum clock delay comes from this stage, then that prevents these other stages from running at their fastest timing, right? And so the max clock delay sort of decides the clock period for the entire system, right? And this breaks down in case of an asynchronous system, so you really don't have to worry about what combination logic goes into here. So for instance, this combination block could be taking 500 picosecond, whereas this could be taking 100 picosecond, this could be taking 200 picosecond. But that would not be the case for a synchronous design, where a lot of effort has to be put in by the synchronous designer to ensure that the combinational block is almost equal, in terms of the time it takes to compute. Okay, so that is one advantage that you can see here. Now, the disadvantage of the asynchronous circuit is now that this done signal, which is the data forwarding signal, is coming from the combo logic. The combo logic is now also having this overhead, extra overhead, to not only compute but also generate this signal, and this is going to be non-trivial. Okay, so this is where actually things break down, as I will show in the next couple of slides. Okay, so now let's go to the motivation. So sometimes asynchronous designs are unavoidable, as many of you know, right? When you have multiple clock domains, some of the interfaces are asynchronous, so you can't avoid it. Okay, in other cases, you have multiple clock domains, you have multi-phased clocks, you have mesochronous systems, and so many other kinds of systems where the asynchronicity is there by nature because of the way the SOC is made, right? So that is the reason why people at least want to explore asynchronous domain. Now, this is one of the emerging areas that was explored quite a bit when SOCs were initially getting or were in research. So this is not for the mainstream computers, but these are specially designed system on chip ASICs, where the clocks are by nature, because of the application, they're all clocked at different clocks. Okay, so how does this system work? So here what happens is that there is a wrapper, as you can see here, which sits around this this interstage buffers, and the job of this wrapper is to connect to the rest of such systems. So you can think of this even like multi-stage pipeline. Okay, so the idea is that this part is locally synchronous. It receives local clock, as you can see here. And when the request comes from the domains, it can be multiple requests, okay, that can be coming from different domains. It will do the job, and then it will tell whoever are, its other connecting IPs that I'm done with the job and you can now take the data, right? So you can have multiple requests coming in, and you could have multiple requests going out, requests indicating that, okay, this job here is done. Right, and then you can have many such domains interconnected with each other, giving rise to what is called as globally asynchronous. Why? Because each of these are connected through these handshake signals. Okay, so here I want to pause and show what this little thing means over here. So in asynchronous domain, the communication happens through request acknowledgement. So the data would come in, and along with the data would come what is called as a request signal. And when this synchronous module has completed its job, it would generate an acknowledgement signal to that domain indicating that its job is done. And then the next set of data can come in. Okay, so each such local module can be locally synchronous module can be connected to many such many other locally synchronous modules at the input and many others at the output. Okay, so that forms a globally asynchronous, locally synchronous system. Now, what are the advantages of such a system? First of all, you can build a very large SoC, system on chip, where each local module can be run independent of the others, and each of them can be run at its own local clock speed. Okay, so you would just have a local PLL, which is nothing but a clock generator circuit, and that would clock this entire domain. Okay, so the global clock is now not required. And global clock distribution, by the way, is very, very power hungry and an area inefficient solution. Okay, it consumes a lot of area because you have to take this global clock tree and the clock has to be taken to all the modules, all the IP cores. Okay, so building smaller clocks or local clocks is simpler as compared to building global clocks. So that is the advantage. But what is the disadvantage? The disadvantage is that this request is now to be synchronized with this local clock. And that is where failures can happen. Okay, so system failures are obviously not acceptable, right? And so there is a long chain of synchronizers, that's it, between this in this yellow box, which is the wrapper, and which takes in this request, okay, to ensure that it minimizes the failure. The failures can never be removed, but they can be minimized to an extent that they happen once in 10,000 million years or something like that. Okay, so very large number, okay, of MTBF, mean time between failure. So so that is how this system works. Okay, so you cannot claim this to be a completely error-free system. Okay, that's what it means. Okay, now what are the key differences in design? As we already saw, that combination logic and the memory latches, which are the registers, are separately designed and then they're combined together. And there is a static timing analysis which takes care of determining the clock period and other things, right? So also there are tools available which takes care of the synchronous logic design, ensuring that setup and hold conditions are met. So it allows a designer to interact with the tool and you can remove the setup and hold constraints, right? Whereas in sorry yeah, sorry. So whereas in case of asynchronous logic design, first of all, it has hazards. Okay, so one has to be very careful with the local timing constraint. Hazards must be removed, and designing becomes extremely complex because now everything is merged. As you can see, the combination logic and memory latches are sort of combined, right? You have to generate the done signal, so you need to know when is the combination circuit going to complete its work, right? And so the circuits have to be designed as delay insensitive or speed independent. So if I have time, I will delve into this. Otherwise, I'll just mention how these circuits are designed in one of the later slides. Okay, so if this is the communication that's happening in synchronous design, we don't have to really worry about this signal, because when the clock comes, this is our clock signal, right? So when the clock comes, if your data signal or the input signal is stable, then it will read the correct values. Okay, so all of these are sort of filtered out. Okay, they are glitches, but they're completely filtered out between clock edges. But in case of asynchronous design, these are not allowed, because asynchronous design is also an event-driven design. So to mitigate that, what is done is we use what is called as dual rail. So what this means is that if there is one signal which is noisy or having glitches like this, then that actually helps here. Okay, so two wires are used to represent one bit here, as it is written here. Okay, so for example, if I want to send a 1, okay, I would have on one wire I would have a 1, and on the other wire I would have a 0. So as you can see here, this is like 1 0, as you can see here, right? And so the two wires are I mean, here we're just sort of representing it. Okay, so two wires are taken together to represent a bit. So as you can see here, these two together, if I look at this combination, it is representing bit 1. This is bit 1. Okay, this is bit 1. This is bit 0 because it is reversed, right? So this is basically 0 1. Okay, And when both of them are 0, okay, as you can see here, when both of them are 0, then you call it as a spacer. So between the two data values, you always will have a spacer. So as you can see here, bit 1 followed by another bit 1 will have a spacer here. This is called a spacer, okay? So when both of them are 0, 0. Now, obviously, if this is the case, then your timings are okay, but now your area overhead is very large, right? Because if you have a 32-bit data that you want to transmit, you would need 64 wires, right? Because of the 2n wires that one needs, right? But it is self-timed, because now you don't have to worry how much time does each bit take, and it's not required that this should be of a certain pulse width, okay? So it is sort of self-timed. That is why the name is asynchronous, okay? So this is the big advantage that asynchronous design will have, which is the dual rail. Okay, now this problem is mitigated through another approach in asynchronous design. So this approach is generally used in what are called as delay insensitive circuits, which are hardly used these days for asynchronous design. Okay, so we will discuss this one because this is more interesting and makes a lot of sense. So this is in fact directly derived from synchronous domain. Okay, so this is called bundle data protocol. In a bundle data protocol, what you have is, if you have n bit data to be communicated, you would have one extra wire. Okay, and this wire carries what is called as a valid signal. So if I look at this wire, okay, so this wire is basically going to decide what is there on this data. So on any of these wires, okay, so if whenever this valid signal goes high, I would sample this value, and at that time the signal has to be stable. If there are glitches here, we don't worry about it. Like synchronous design, we just have to ensure that everything is stabilized by the time the next valid signal comes. So as you can see here, all of this is fine. It is acceptable in a bundle data protocol. But when the valid signal comes, that is when the data has to be stable. So if you see this, it appears to be very similar to synchronous design, right? So this became a little bit more famous in the asynchronous community because of its similarity with the synchronous domain. But there was a big catch over here, okay? There was a big issue with this, okay? So the big issue is the generation of the valid signal. See, in a synchronous design, it is a clock signal that decides when we are going to sample, right? But when it's a bundle data protocol, it's this valid signal which decides when we are going to sample it. So let's say I've generated a valid signal here. Now, when do I generate my next valid signal? How do I know how long is this glitch going to be there, or or these effects are going to be there? So it basically means that, okay, I have to take the combination logic. I have to study what are how much time is it going to take to complete the computation. What is the worst case delay that it is going to take, and then I have to generate the valid signal accordingly. Okay, so the benefit is that I need not generate the valid signals at equally spaced duration. So my combination logic itself can have any timing, but unlike self-timed circuits, which gives average performance, I will talk a little bit about that aspect in a moment. The generation of the valid signal is now required because you have to study the combinational circuit and you have to find out how much time does this combinational circuit take. So for example, let us say that the first combinational logic takes 500 picosecond. So I can generate this valid signal after 500 picosecond. Now if I don't know if you have heard about what is called as variations in a chip. It is called process variations. Okay, so when you manufacture something, and you say, okay, this is an adder unit which adds at 100 picosecond. Okay, this 100 picosecond is sort of the worst case time that the adder would take, okay, for a given process in which it is fabricated. Okay, but if it is fabricated well, let's put it that way, in a fast corner, for example, then it would take, let's say, 50 picosecond. Okay, but that benefit of having that fast adder is completely removed in this bundle data protocol. Okay, whereas in the previous slide, in this slide, when I talked about dual rail, it is a self-timed system. So in a self-timed system, if my adder has completed its job early, then the done signal can be generated early and my processor can actually run faster. Am I making sense here? Is it clear what is going on? So we have like two systems. Okay, one is an extremely, I would say, asynchronous, completely sort of asynchronous. And then the second system is like, asynchronous in nature, but more similar to synchronous design. Okay, something like that. Okay, so I'll pause here for a minute and see if there are any questions. So insofar, whatever we've discussed. Yes.
What is meaning of bundle data? Means data will be independent now. Means bundled means what?
Yeah, so this bundle data actually stands for this n wires together. Okay, so here one wire is representing like the bundle of n wires. So what it means is that if there are n wires, then we have to wait for, you know, the worst of these wires. Okay, so let's say if you have a 32-bit bus, then all the 32 wires have to settle down before the next valid signal can be generated. That's what it means. So you are sort of bundling this 32 wires into a single bundle. That's what it means.
Means bundling means buses. Means
Yeah. It's like a bus. You can think
okay.
of it as a bus.
Okay.
Yeah. So this bundling is not there in a self-time system because there every wire is like treated independent. So there, for example, each bit, if it's a 32-bit bus, then each bit is like 2n wires. Okay, so I would have a bus of 64 wires actually, whereas it's carrying only 32 bits. That's what this means. Yeah. Any other question?
So is it something like each bit is like clocked separately?
No, each in this example, in this dual rail system, or in this one. Okay,
Yes.
see,
In a dual rate.
okay, in a dual rail, there is nothing like clock. So think of it conceptually like this, that suppose I have, you know, an adder connected to, let's say, maybe a multiplier unit, okay, or some logic block, okay. So I know that in a processor, whenever I have completed addition, then only I want to send, I mean, then only the next block should respond. Okay, so I'm just giving a simpler example here, but it could be any such block. So if you have two stages that are connected to each other, we know that if the stage one had done some addition, and if the results have changed, then only that those results have to be passed to the next block, and then the next block can compute based on the results that we have obtained just now, right? So if the data is not changed, then there is no need of computation, right? So here what it is, what this is saying is that, so you can think of it like only data path. You know, there's nothing like a control path actually. You just have you know, the data path and the control path are sort of mixed up with each other. Okay, unlike the synchronous, I think yesterday you had a talk on processor design, right? So we understand that the data path is independent of the control path, right, when we design it. But here it's actually linked because you are finishing your addition, and then the changed data is like a signal to the next stage saying that, you know, I have completed my job. Now you can take this changed data and operate upon it. So that is why the overheads are very large in this kind of a system. Is it okay?
Yes,
Yeah. In a bundle data, this problem goes away because you just have a valid signal. So the second stage comes to know that I'm getting the new data when a valid signal comes. So the valid signal can be thought of like a clock replacement for a clock for an asynchronous design. Okay, now since we have talked about this, there is one interesting thing also to understand about this average case performance. So one of the major reasons why people wanted to explore asynchronous design was people understood that when I'll give an example of addition because that's everyone uses that, right? So we know that when we add 0 plus 0 for any adder, whether it's a 32-bit adder or a 64-bit, any bit, any n-bit adder, we know that 0 plus 0 is going to take minimum delay, minimum time, and all f's, all ones added with all ones is going to take the maximum time if it's just a simply ripple carry or any similar such adder, right? So in a synchronous design, we would always, you know, give the delay to the adder based on the max delay, right? Which is all ones being added to each other, right? Together. Whereas in case of an asynchronous design, based on the data the timing gets decided. So if I'm adding zeros for most of the times, then my system will actually outperform synchronous design, because the throughput will be very high. All the time it's taking less, because the moment the addition is completed, I can just move on. Okay, so the expectation actually from the asynchronous design was that if I'm adding numbers which are small numbers, let's say, or I'm just giving an example of addition here, but any such unit, okay, which has a large delay variation, okay, based on the data input, then such systems will benefit more by asynchronous design than synchronous design, because asynchronous design would give average case performance, okay, average case performance, which is data dependent. And this is not there in synchronous, because in synchronous, the worst case data is always used to find out the delay. Always, for any compute circuit, right? We would take the worst case delay, which comes from the worst case data input, right? For that particular compute unit, right? And so that was the motivation for async. But when we actually started to design, it's sort of started to fall apart, and never, so when the processor was eventually designed, I think there were several attempts at that time, one from Caltech, one from USC, and I think one from Manchester. So there were several attempts in around 2000, and different processors, MIPS processor, ARM, which is called as Emulate in Manchester, and such processors, when they were designed, it was in fact found that the area overhead was so large that we could not beat the synchronous version, okay, because of dual rate. And then came this bundle data, which actually showed much better area efficiency. Okay, now I will skip a couple of these slides in the interest of time. So I'll just talk about the bundle data protocol, because this is what will make sense if at all anyone has to go asynchronous. Okay, so here is how it would work. Since synchronous designers already have data path and control path separated from each other, we are leveraging that over here. Okay, so what we will do is we will simply remove the clock, keep this data path as it is, intact as it is, and remove the clock. That means the ISBs are now sort of replaced by these control circuits. They're called as handshake controller. Okay, and the way it will work is, whenever the previous stage has completed its job, the previous stage would generate on its control path, okay, would generate a request in, and then that would give a start signal to the data path, and then the data path would take this data and compute and generate the data out as well as the done signal, and then the request would be gone out. Now this also is actually not very convenient to use, and so what is typically done is this start signal is connected to a long chain of buffers which mimics the data path delay. So if the data path delay is, let's say, 1 nanosecond, okay, what is done is that start signal is nothing but the start signal and the done signal are sort of connected by a long chain of buffers which generates a delay of 1 nanosecond. So it's more like a self-looping kind of a thing. So you're simply saying that I generate a request, then I wait for 1 nanosecond, and then I generate the request out, assuming that by that time the data out would be ready. This is how the bundle data protocol is implemented in real life. Okay, so I will now show what what can be done. Before we go there, there are some important elements that we must study when we look at asynchronous design. One of them is a C element. I will not go into the detail of this element in the interest of time, but if there is time, I'll come back and discuss more if you want to understand how circuits work. But the basic idea is that this element is crucial to designing the asynchronous system. And why it is crucial is because this is a new element where the output is going to change only when both the inputs agree on each other. Okay, so you don't have any such logic element in the logic family of synchronous, for example, logic family. Okay, so it is it is an element which is also acting like a latch. Okay, so it's a combination of both of them. So you can see that when A and B are agreeing, so if both of them are 0, the output will be a 0. If both of them are 1, the output will be a 1. If they disagree with each other, then the output is just maintained as it is. Whatever is the previous value is just maintained. Okay, so that is the beauty of this this C element. It's a combination logic in some sense because it is having this truth table, but also it maintains its previous state. Thus, it can be used as a latching element also. Okay. And there are some other implementations of C element. Okay, I will just show this one diagram to explain why dual rail logic was, very complicated to use. Yeah, is there any question in the meanwhile? Any question? Okay. Yeah. So, this is an example that will explain why, dual rail logic was almost impossible practically. Okay. See, as you can see here, in a dual rail logic, each wire is a bundle of two wires, right? So there are, these are all the inputs that we have. And then all the outputs that we have are actually passed through what are called as the OR gates, okay, which are nothing but indicating that the job is done. Okay. So for each of the wires, they have settled to the correct value. That is what this is actually indicating. Okay. And then if every wire has settled to its correct value, that's what this tells, then these can be connected through the C element. Okay. That is, which is what we saw earlier. And this generates a done signal. So you can imagine the amount of overhead, right? First of all, the entire logic has to be evaluated, and then a large C element, or sometimes a tree of C element, would be required to detect this completion, that okay, the job is now done. And this was the main killer in the dual rail logic, and that is why this was not used as much, unless the asynchronous logic part was a small logic. Okay. All right. So yeah, now let us go to the processor design. Okay. So this is the work that we have done recently in our lab, and I will show some of the interesting results that we have got, and which is also the motivation for going asynchronous for certain very niche applications. Okay. So we have taken here as an example a simple Dlx processor, and we have tried to convert that into an asynchronous design. Okay. Now, before I start talking about this, I want to mention one or two important aspects about ASIC design. Okay. So when we start designing something like a processor, I think yesterday you had a lab on RISC-V implementation, right? So as you all know that, if you have to design RISC-V, you have to use something like System Verilog or Verilog, where your ASICs are going to be synthesized, right, for a given technology node. And then you will have a separate set of tools which will allow you to simulate and check whether your circuits are actually working fine, right? And then if all the test benches are all correct, then you would go on to the next set where you would do the verification, or rigorous testing and verification that okay, now the processor works fine, right? And all test cases, people use formality or some other tool to check that okay, all the cases are covered, and it is completely verified system, right? So all of these, so basically the underlying thing is that if I have to design anything like a RISC-V processor or a Dlx processor or any other MIPS processor, something as an academic setting, the primary thing that the minimal, you would need would be a tool, right? So without a tool, you cannot begin, right? Now, one of the main bottlenecks for asynchronous design is the non-availability of tools. When you start designing something in dual rail, for example, there are hardly any industrial tools. Okay. So people have to rely on academic tools, which are obviously not very, which are very hard to use because there is less support and, not very nicely tested. And so many such issues are there. Okay. So one of the major goals of asynchronous design community is to come up with tools which are based on synchronous tools. Okay. So it will be an asynchronous design using synchronous design tools. Okay. So that is one of the major interventions that the async community wants to first make. Okay. All right. So this is a two-stage Dlx processor that we have implemented in our lab. So we have taken this code, it's available online, and we just downloaded the Verilog code, just cleaned it up a little bit, and implemented our own clock tree and other things to get this whole processor. By the way, this is also, when I say clock tree, we have to bring in the clock tree because it's not at the Verilog level. Okay. So we have to synthesize it, and then we have to lay it out, and then we do what is called as a post layout synthesis, and then this Verilog code is extracted. If you have any questions, or if you want to know more about it, we can discuss. Okay, once I'm done with this. Okay, so now when we come to asynchronous circuits, this clock goes away, and we have the handshake protocol, right, which is nothing but request acknowledgement. So we have used what are called as click controllers. These are very interesting controllers and proven controllers in some industrial settings. So we have just taken the click element, and what it does is that it just generates something like a clock signal, okay, based on the request acknowledgement. And as a stage completes its job, the clock is then transferred to the next stage, and this keeps on happening. Okay, so this is how the data would also progress. Okay, so let us see how how the click controllers are compared with respect to each other. So first of all, we must understand that the overheads that we are now going to pay are in terms of these extra click controllers, right? So we had first synthesized them and found out what is their area and what is their power. Okay, so as you can see here, the click controllers take significant amount of area. Okay, just different technologies, just for comparison. Okay, that how technology will play a role. Okay, so it's just to say that, okay, we have synthesized in multiple different technology nodes. Okay, and then just comparing between the two inverters and buffers that one can use. Okay, sorry, I think there's a typo there. Yeah, and then we have also done the technology comparison for power. Okay, so this is the same click controllers with multiple power components. As you can see that there is a significant amount of power that goes into the click controller, right? So I mean, when I say significant, we are our job is to compare this with the clock tree power. Okay, so that's the eventual goal. Currently, it's a study that's going on. Okay, so our goal is to minimize the click controller power so that we can benefit, when we remove the clock tree. Okay. Okay, now when we go to the synchronous RISC processor, which is this Dlx or the Dlx processor, then what do we have? So we have two stages: execute preprocessor and the ALU stage. Okay, so these are the two stages. So we first make a top module and then call these two stages in the single Verilog file. Then we have a clock tree synthesis done, the reset tree synthesis done. Then we attach the inputs and the output modules to it so that we can do the testing. This is all automated, by the way, the testing and all. And then we implement the same thing using asynchronous technique. Now I've just called it as technique 1 over here because this was an incorrect implementation, and I will show you why this is important to discuss. Okay, so what we did is we just simply took the processors, we took the interstage buffers, as you can see here. Okay, and the only change we made was we added click elements, which are the click controllers. Okay, so these are now generating the clocks for this processor. This is a completely asynchronous processor. Okay, and what we figured out was that when we gave this file, okay, so this file was simply given to the tool, and when we started testing it, okay, we figured out that the timings of this clock were all messed up. Okay, and it took us some time to understand what was going on. So we figured out that these timings, the T critical was all getting messed up when we were just giving all the files as a single, Verilog code and allowing design compiler kind of a tool to synthesize it. Okay, and that is where we came up with what we call it as technique 2, or the corrected technique, I would say, where what we have done is we have synthesized. Now this is the most important part of this project, which is that we synthesized the stage 1 and stage 2 independently and run it at the maximum clock. And then when we went to the top block, we had a set don't touch. That means the Verilog code, which is a synthesized code, was not allowed to be changed by the design compiler. And then the code worked perfectly fine. Okay, before that it was giving errors. Okay, so this is the correct results that we have got. As you can see here, the takeaway here is that in an asynchronous setting, the cell count is very high, which means the area is actually very high. Okay, as you can see here. The sequential components are almost similar because we have not touched much over there. Some additional components just for the input and output token generator, which are necessary, by the way. And as you can see, the area is higher, okay, for the async part. Okay, for power, what we observed was it was low. So there was obviously this, we were thinking, what is happening here? Why is it that area is more and power is less? Okay, so that was one question that we had, and this was a consistent observation. As you can see here, for 65 nanometer also, you can see that the area is more and the power is still less, right? So what we figured out was the following. So we understood that so as you can see here, there is a large amount of internal power that is being consumed in a synchronous setting as compared to the asynchronous setting. Now, these two powers are actually related. Okay, so internal power basically means a short circuit power. So when anything switches, okay, when elements switch, so there's a large switching activity that is observed in synchronous case as compared to the asynchronous case. And this is to be expected because when we look at a clock signal, okay, even when the data does not change, when the clock transition happens, many many registers are going to actually see the switching activity, and that was one of the observations that we made. The other parts were not changing much, and so we could say that the lowering of the power was mainly because the clock signal switching was avoided. Okay, so that was the advantage that we got from the asynchronous design. Okay, and so this is the summary of what we have done. So it was our first attempt to design an asynchronous processor completely from scratch. We have also completed the design of asynchronous RISC-V, which is what what was presented yesterday. And we are expecting a low power processor, but of course more investigation is required here. And we have designed what is called as a radiation hardened asynchronous processor. So soft error resilient asynchronous design, SERAD, which is one of the works where we actually showed that it is not only low power, but also it is much more tolerant to errors as compared to its synchronous counterpart. Okay, so I think I will stop here, and if there are any questions, I will take. And if there is a little bit time, I will talk a little bit about SERAD also. Yes, please.
Excuse me, ma'am. So radiation hardened in the sense, is it like side channel resistant or?
Okay, so radiation hardened means the circuits that are used for space applications. So when we have to design circuits for space applications, these circuits are subject to many cosmic rays. In fact, I have a short presentation on that, but I think my time is up to 10, right? So yeah. So anyway, so what happens is that when we design circuits for space applications, there are rays which go inside the circuit, okay, which means transistors, and then these transistors have unwanted glitches. Okay, so they are soft errors. Sometimes there are hard errors also, but we are talking about soft errors here. Soft errors means that there is a glitch of a short duration, so a short pulse is generated. So it is like saying that when a radiation particle attacks a circuit, for a small time, some charges are created in the circuit, and once those charges are diffused, then the circuit recovers. Okay, that's why it is a soft error. Okay, it is not a permanent error. And the problem is that this soft error can result into permanent error. For example, if there is a wire which is, let's say, having this soft error, and if a flip-flop latches the value when the error happens, then it is a permanent error, right? Because now you have sampled a wrong value because you sampled it at the time when the error has come. Am I making sense? Is it like clear?
Joycee, you can go up to 10-15.
10-15. Okay.
Yeah.
Okay. Okay. So maybe maybe I can talk a little bit about. Maybe I will skip these slides, because I may not be able to cover all of these. But something, something that will.
I have a question. I have a question.
Yes.
Ma'am, how are you comparing? How do you calculate the area and power in synchronous and asynchronous? Can you tell a little bit about that?
Yes, sure. I'll in fact use this example so that I can. Okay, I'll just skip. Sorry about this. So I'll skip these slides where I've explained how this processor was designed, and I will go directly to the So I think this will help us to answer your question also, and I'll also explain how we have done the sync to radiation hardened. Actually, I should say radiation hardened sync, and then from there async. Okay, so all the questions I think I can take here. So are you aware of like Verilog and System Verilog kind of?
Yeah.
Okay,
Yes.
okay. Yeah. Okay. So this is a typical ASIC flow, as you can see here, right? So we would have a gate level netlist. And then for a radiation hardened system, if whether it is synchronous or asynchronous, one has to make some changes. Okay. Otherwise, your system cannot be made soft error tolerant. Okay. So this is a parser that we have written in our lab where we take a gate level netlist. So gate level netlist is just a Verilog file. Okay. And Verilog file which is synthesized at a particular technology node once the standard cell library is fed into it. So this is so suppose you are working at let's say 65 nanometer, then you would have a standard cell library for 65 nanometer. Okay, so that is fed to the synthesizer, and what you get over here is a gate level netlist. So you'll have AND gates, flip flops, and AOI gates and other such gates. Okay, so that's the netlist with which we begin. And then this is given to a parser, which basically converts this whole synchronous design into a radiation hardened synchronous design. So what happens is when we do this, there is a issue that we may lose timing. Okay, because we have earlier synthesized it at a certain frequency, right? But the moment you convert it into any other form, and this form is basically adding some more gates so that you make it soft error tolerant. Okay, so radiation hardened is also like soft error tolerant, or we don't have soft errors in such a netlist. Okay, so when you sort of do this, you have to resynthesize it, because you have to meet the timing afresh. Okay, so that is one reason. The second reason is now there are custom made cells that has to be integrated along with the standard cell library. So one custom cell that normally gets integrated is the C element. In the previous slide I talked about the C element, right? So one of the elements that is there is a C element. There is also another element which is required, which is called as the flip flop. Okay, so the flip flops that we use for normal synchronous design, like D flip flop, for example, they cannot directly be used for such design, radiation hardened designs. So you have to design new flip flops. One of the flip flops which are very commonly used by ISRO, for example, is called dual interlocked cell. It is DICE cell. Okay, so that these cells get replaced actually. Okay, and so you have to resynthesize it to get the new timing, and then you would do functional verification by giving radiation inputs at different nodes to check whether the designs are completely resilient and there are no errors because of the radiations. And then you would sort of synthesize it to meet the timing constraints, and that would give you the final synthesized netlist. Now, as you can see here, area, power, and delay are the outcome over here. So you are asking this question, how do we get the area and power, right? So if you have used design compiler DC, because we are using that, but you could have used also any other tool from, let's say, Cadence or Mentor Graphics. Any other tool also is fine. When you do the synthesis process, this is actually given as the output of the design compiler. Okay, the question is not about the values that are given. The question is, how do you verify whether the values are correct or not? That is a more important question. So what we normally do is, before we can agree that these values are correct, we generate small test circuits. Sorry, we design small test circuits where we know, how what power is expected. So I'll explain how the flow is. Okay, so suppose I'm making a simple benchmark circuit. Okay, so let's say I'm making a small, let's take an example of adder or a comparator. Okay, suppose I've made a comparator circuit. So I know that the gate count in this circuit, right? And once I give the test bench inputs, I also know how many how many gates are going to switch. Okay, so this standard cell library actually has the power values for every gate. Okay, so when a NAND gate switches from 0 to 1, how much power will be consumed? That is written in the standard cell library, which is provided by the foundry. Okay, so if I'm using, let's say, 5 NAND gates, and if 3 out of them are switching, then I can manually calculate what power it is going to take. Is this clear what I'm saying? Is it making sense?
Yeah.
Yeah, so this number has to be verified. So you have to be sure that your synthesis procedure is correct. And so we take a design which we know, and where we can count exactly how many switching, how many times nodes are switching, which nodes are switching, and then we would compare the numbers that we get from DC, that means the design compiler, with the values that are there in the standard cell library, because these values are simply added to get the final power. Is it okay? And for area also, so the standard cell library also has another file which is called as LEF file, layout exchange format. So this file contains the area for every gate. Suppose I have an AND gate, how much area is it going to take? Okay, so if you have a cell count of, let's say, all NAND gates, then you can say this is the total area that NAND gates will take. Okay, so DC does this for us. So we don't have to sort of calculate the area, but we always give a small circuit as an example and then we test it. Now, one important thing to keep in mind when if you're using design compiler, let's say suppose you are also working with ASIC design, one very important thing that is sometimes missed out is that when DC reports power, this power is not always correct. Okay, so you will get the correct value of power only when switching activity file is added. I don't know whether you have come across these terms earlier or not. So how this works is for every processor, when you're testing it, I think yesterday also Neil was showing test vectors, I mean test inputs, right? So when you're testing your RISC-V, you will give some test bench to the to your synthesizer, right? To a tool like, let's say, Model Sim or something like that. So once you give the test inputs, the entire circuit will respond to it. And then what you get is the final output, right? So whatever added output or whatever load, store, whatever instruction you're executing. When you do this, all the internal nodes also switch. Okay, and so this tool generates what is called as a VCD file, voltage charge dump file, okay, which is nothing but it tells you which all internal gates are switching. And this file is converted into a switching activity file. This is a very important step because if this step is missed out, then the power calculations are all messed up. Okay, so if any one of you are doing ASIC design or trying to use a design compiler, this is a step that we initially did not understand what was going wrong, and then it took some time for us to figure it out. Okay, so if you are doing research in this, then this is something to keep in mind. And I think this is also true for Xilinx, Vivado, or any other FPGA based tools also. Okay, so every time you find out the power, you must give what is called as a switching activity file, because then the tool will give you the correct power output. Okay, and also the correct delay output. I think generally area and delay are properly calculated, but I have seen that power calculations are not always correct if the switching in activity is missing. Okay, so does that answer your question?
Yeah, ma'am. Yeah. Thank you, ma'am.
Okay. Any other questions that you have? Others, I'll just go to the final results and we'll stop. Okay, so we have, as you can see, done a lot of simulations. So this is what I wanted to show. So we have taken a plasma processor here as an example. It is a 3-stage processor. Again, it is available on opencourse.org. And what we did is we first designed the synchronous plasma, which is, again, a sort of revised version of what is available on OpenCourse. And we synthesized it. And then we applied other radiation hardening techniques, which are very well known in the literature for radiation hardened work. And we then designed our own plasma, which is the asynchronous but radiation hardened plasma processor. Okay. And what we observed was that this area was somewhere in between, here. That means it was definitely more than double, twice that of a synchronous plasma, but it was doing better than the technique that is used in most of the space application centers. Okay, so for example, ISRO, people use TMR technique as the most commonly used technique. Okay, so we figured out that it was doing better in terms of area with respect to this technique. But the interesting thing was it was actually doing much better in terms of frequency as compared to the existing technique. So that was the main advantage of this work. Okay, so that is the result that I wanted to show. And yeah, so these are some of the references that were referred for this particular work. I have not gone into much detail over here, but if you are interested in this kind of a work, we can discuss more on it. Yeah, so I think I'll have to stop over here. And if there are questions, I will take.
Ma'am, how does frequency between an asynchronous processor and synchronous processor compare? Can we take them at their face values?
Okay, that's a really good question. Okay, so first of all, I think the question should be, where did the frequency come from? Because there was no clock, right, as such. Okay, so yeah, so there is no clock here. So what we are doing, because we want to compare, what we are doing is we are taking, so in this example, in case of plasma, there are 3 stages, and we know that one of the stages is the slowest of the 3 stages. Okay, so what we have done here to report these numbers, what we have done is we have taken that stage and first found its critical path delay. Critical path delay is the max delay, which is what DC gives us. Okay, and to this we have added the delay of the controller, which is again independently synthesized in Cadence. And it's, so we have basically used many tools here, okay, in this work. So a part of the circuit is implemented in Spice, let's say, and a part of it is implemented in Verilog. Okay, and for getting these numbers, we have done the worst case analysis. So what we have done is we have taken the stage which is the slowest, okay, and taken that frequency. I mean, taken the worst case delay from there, and then we have taken the Spice netlist based, again, the worst case delay for the controller, and we've added them together. And that is what gives us this frequency. Is it?
Yes, ma'am. Okay.
Any other questions? Okay, so then I guess I can stop sharing my screen. Yeah, and over to you, Mr. Madhura. Yeah.
Thanks, Joycee. That was a fantastic talk. I think all of us are very excited to see what we can do. The especially this talk coming right after RISC-V and your work on RISC-V as an asynchronous processor. Thank you very much, and I think some of us will get in touch with you if that's okay.
Yeah, sure. Yeah, yeah.
Thank you very much. And I think if I look at the schedule, we have Manu next.